different on this computer. Let's hide these guys. All right, so let's finish talking about threads and get us going on Unity. So last class, we finished implementing our merge sort and with the double recursion, and we kind of talked about how this is it's an example of what's typically a difficult algorithm for beginner and intermediate, and I mean even advanced programmers. Merge sort is not this trivial thing, but it's a really good algorithm for kind of testing your current aptitude in programming, because that what I think I mentioned, you'll see it again like basically every single year, and each time it should be less and less intimidating, and hopefully by the time you're a senior, you don't love merge sort, but you're like, okay, if I had to do it, I can do it. It's not the end of the world. So that's the why we look at that example in here. I think I mentioned that on an exam, I won't test you on like write merge sort, so it's not that important to me that you completely understand the algorithm from a test taking perspective, but it's a very good algorithm for showing what's called divide and conquer algorithms, and also algorithms that are compatible with multi-processing, multi-threading, which is how we're going to make that connection today. Okay. Looks like last time, probably near the end of the class, we started talking about something called IPC, interprocess communication. So we can think of threads as being similar to this. When we first introduced threads, we mentioned that they're kind of lightweight processes, where you can think of a process on an operating system as being a representation of a running application. So every single time you double click on an application to launch it, a process is born. The reality is, as modern computers, every process has a starting main thread. So internally, even modern operating systems, yes, they still create a process for every program running, because these are all Unix-based operating systems. And the idea of having a heavyweight process that has a lot of information from memory usage and CPU time allocation and things like that associated with it is still commonplace. If we're going to write a multi-threaded application, it's a lot safer for us as developers to do that through threads, or a multi-processing application. It's a lot safer for us as programmers to do that through threads rather than through processes, just from a perspective of making sure we don't take over all the computer's resources when we have a bug in our program. Okay, so there's a lot of stuff in operating systems today that protect us from ourselves. So there isn't a huge risk of that today. Most of our applications run inside of a virtual machine anymore, or at least a virtual ecosystem where the most damage you can do is just to your little virtual pod, and your program crashing is not going to impact other things in your operating system. At some point, I probably mentioned maybe last semester when we were looking at C++, that, back in the day when I first was learning, to program, when I was first learning C and C++, it was entirely possible. You have a little bug in your program, you have to restart your computer because you've overwritten half of the stuff in running memory or something like that. So that's another thing we can kind of appreciate today. All right, so having said all that, we want to look at today just the couple of ways that threads can talk to each other, just so you get a feel for that. And then I'm also going to use the opportunity, as we're talking about that, to kind of introduce the concept of that game loop that I referenced last time from Unity. So just real quick, I know I mentioned that I had a link up on Blackboard for this, but if you go to Unity, I think is it Unity 3D or unity.com? Yeah, so if you go to unity.com, this site, and you go to download, and right here, actually it looks like it defaults to download for Windows because I'm on a Mac right now, but download it for your particular platform. and then get it installed on your computer. When you install it, it's going to install Visual Studio, all sorts of stuff like that. It's about a 10 gigabyte download. So if you haven't already done that, I think it would be in your best interest to go ahead and do that over this weekend. So you have Unity all installed and ready to go, because we'll start actually writing stuff with it on Monday. So if you want to kind of follow along, or at least come back with some questions if some weird stuff happened. If I go, once you install it, you'll end up with this thing called the Unity Hub, which is launching here in a sec. So you'll have something like this initially. What you won't have, oh, it looks like there's a new version of Unity Hub. That's fine. Initially, though, you won't have any version of Unity installed. So when you go under installs here, you can click on official releases. So right now I have 2022 3.10 F1 is the newest version I have. If you went to install editor, yeah, you see that. You probably want to look at the ones that are under official releases. I probably mentioned last time that for what we're doing in here, it actually probably doesn't matter what version you have, but if you want to be as compatible as possible, get this version, the newest version of the long-term support one, for your particular processor. I'm on a newer MacBook Pro running a M2 Max, so I'm on Apple Silicon. That's the kind of processor I have. Where most of you probably have an Intel processor on your Windows machine or your Mac, unless you have a very new computer from Apple. So download the right version for you, but this is the 2022.3.17 F1 would be sufficient. I'll update to that later on today or something, but I'm running just a micro older version of that. I think instead of 17, what it was, mine 10. Yeah, mine was 10. So I'm just typically the last number is the least significant. So just a couple of updates old. But I'll get it so I'm equal to what everybody else will have. So do that over the weekend. That way you have it good to go, and we can start looking at that on Monday and actually start learning about it. All right. Any questions about getting Unity up and going for Monday before I go on and finish up with threads? Okay. So, and if we just work backwards a little bit, so let me just talk Unity world a little bit more so we kind of can fill in this gap of where we're going. So Unity, this is a game engine, which effectively means this does all of the physics stuff for our games so that we don't have to do the math. And on top of that, it adds the standard things that all games have. Now, we can probably list a couple of things that all games have, but the piece that's most important to us right now is the idea of something called the game loop. Okay, so the game loop is a section of code that runs every frame. Where a frame is, if you're a gamer, especially PC gamer, one of the things you'll do is you want to make sure your games are running at least 60 frames a second, or 90 frames a second, 100 frames a second. That's the reason why PC gamers go out and buy the newest, latest, greatest, expensive graphics cards. A majority of your games, a majority of the time, can run on an older, cheaper graphics card. What it really comes down into is when you're playing a game and the game has the most stuff going on in a moment. If you're on an older graphics card and you go into a really crowded area that has lots of explosions, lots of stuff happening on the screen, things like that, your frame rate might drop from 60 down to like 2, which at that point you're looking at a slideshow. So when we think about frames per second, what we're really talking about, if you've seen those flip books, it's how many pictures in a row do they show in a single second to make you believe it's motion video. That's what a frame is. So typically, like a movie is running at 24 to 30 frames per second for if you're just watching normal movies. For gaming, I would say kind of the bare minimum for our modern monitors is 60 frames a second. When you go out and buy a computer monitor, a non-gaming specific monitor would probably be a 60 hertz monitor. And a monitor that is 60 hertz means that it has a refresh rate of 60 hertz, which means it can show 60 frames a second. So even if you have a graphics card that's pushing 100 frames a second, if you have a monitor that can only show 60 of those, that's all you're ever going to see. Most PC gamers, so for those of you in the audience here that are PC gamers and kind of know about the stuff I'm talking about here, when you went out and bought your gaming monitor, you probably got at least a 120 hertz monitor or a 240 hertz monitor. There's some debate. The human eye can only see something in the ballpark of about 45 frames a second. So then you start getting into these interesting discussions related to, what's overkill for your computer hardware. If our eye can only see 45 frames a second, then isn't a monitor that shows 60 frames per second enough? And isn't a graphics card that at least maintains 45 frames per second enough? The answer is to all those, yes, it's enough, but there is a perceivable difference, especially from like a smoothness perspective, for games that are running at a higher frame rate, even if you're only able to experience it at a lower level of that, limited by your whatever your monitor is or what your graphics card is capable of. So if you are like an esports player and you play these competitive games where, the blink of an eye can make the difference or something, I would say that most competitive gamers can tell the difference just from a smoothness or even just kind of a feel between a higher frame rate and a lower frame rate, even if both of them are faster than technically the human eye is supposed to be able to see. And the reason why gamers might get these super expensive graphics cards is not for the average case, because even an average graphics card can probably handle most of our modern games at the average case. But it's when you go into an area where there's a lot of stuff happening at once, a lesser graphics card will drop your frame rate down to really slow and the game becomes unplayable. Where if you have a graphics card that's running your game at 400 frames per second and you go into the busy area and it drops to 160 frames a second, you're still happy. So that's the reason why you have overkill. If you want to think about it in terms of buying a vehicle, you don't need a V12 engine when you're driving on residential streets. But if you ever find yourself in a situation where you're drag racing somebody on a straightaway, having the bigger engine might be of benefit to you. Something along those lines. All right. So swinging back into reality, that was more of the geek piece of what a game engine's ultimately accomplishing. We have this thing inside of Unity, inside of all game engines, called the game loop that's attached to every single script, and that'll make sense when we start looking at it. But effectively, we have an opportunity every single time a frame is rendered on the screen. We have an opportunity to interject some logic. All right. So if you want to think about this from if we're kind of hard coding this, if we have a little box on the screen and we want it to move to the right, we might move it to the right 3 pixels every single frame. And if it's showing 60 frames at a second, you'll see that guy mostly smoothly moving over with, maybe a little bit of jerky type action. But when you use the standard game loop, which just shows on every frame, at that point, you're not actually dealing with your game isn't going to work the same on everybody's computer, because different people's computers with different graphics cards might show more or less frames per second. There is a version of the game loop where you can lock it to 60 frames a second, for example. So as long as whoever's running your game can maintain at least 60 frames per second, they're going to have the same experience as somebody who might be capable of 200 frames a second, but you're only doing something every 60. All right. But in any case, from our perspective, connecting this to threads, we have this thing called the game loop, which is a section of code that runs every single frame. Okay. This is implemented using threads. All right. So let's kind of leave it at that for the moment. We'll talk about that more as we're able to dive into Unity specifically. All right. So if we think about merge sort with threads, let me just go back to my original merge sort example here. Actually, I'll steal from down here. What we want to do is we want to think about merge sort here, where we want to replace our recursive call or recursive calls in the case with merge sort, with spinning up threads to go and deal with the portions of the array. All right, so I'm going to kind of mix this guy up a little bit here. Zero, go with that. All right. Let me just get a couple of these variables out of the way here. All right, so we make our initial call to merge sort right here, calling merge sort, passing it the entire array, the beginning and end, 0 and 4 is the last legal bucket in my example here. We say, is this guy trivially sorted? The answer is no. Why? Because begin and end are not the same value. So under normal conditions, what we would do for the original merge sort is we would call merge sort on AR from bucket 0 to bucket begin plus end, 4 plus 0 divided by 2 to 2. And we'd also call merge sort on bucket 3 to bucket 4. So this is call merge sort on the left half, call merge sort on the right half. All right. So now if we're doing it this way, move this up a little bit. You know, we talked about the whole recursive model last time and stuff like that. This call to merge sort will block us getting to this call. All right. So we're going to, the way merge sort would work through recursion is we would go and whittle down this whole left half of this array and get that guy sorted before we even start on the right half. But now I'd ask the question, we kind of talked about some of the weaknesses of merge sort last time and saying, okay, it's memory inefficient and you know, it's also not necessarily that fast if you're running it on a single processor machine, not running it using parallelism. This call to merge sort is not going to happen until this call finishes, which means that this call has to finish. Actually, it would be this call would have to finish, and this call would have to finish, and this call would finish, and this call would finish. So there's a lot of calls to merge sort that are just sitting there waiting for their turn to do something. But let me ask you this question. Now, if you remember, the last step of merge sort is the merge piece, where we would ultimately have this side in order, and we'd have this side in order, those two halves. And then we would merge them together to get your final sorted thing. So when the first call to merge sort here, when we call in the left half, that guy's entire job is to just put the left half of that list in order in and of itself. The second call puts the right half of this list in order. Okay. So now, is there any reason why both of these, while that half can be being sorted and this half could be being sorted, at the same time. Recursion didn't allow us to do that just because of the nature of blocking calls. But is there a good reason that I couldn't hand one of you in class this half of the array and tell you to go sort that, and then hand somebody else from class this array and tell you to go sort that? And only once both of you return and say, okay, we've done our job on our halves, then we can do that final merger. Okay, so there's really not a good reason why we can't have the left and the right half being sorted independently and simultaneously. All right, recursion does not allow us to accomplish that. We're at the mercy of the operating system, and recursive calls block. But we could modify our merge sort where instead of making the recursive calls, we instead spawn two threads. So if we assume, call this guy multi-threaded merge sort. Assume that a thread's job is to perform the merge sort, including the merge on the portion of the array that thread has been assigned. So assuming that's how threads work, we can create a new thread, passing it the array, the begin, well, let's just say the array, begin, and end for the portion of the array that thread is responsible for, rather than making a recursive call. We just need to ensure that we don't start a merge step. So that second step where we merge two halves together, we don't start a merge step until after the threads have finished for the left and the right halves. Okay. So really, when we spawn off these threads, we're really thinking about this in terms of replacing recursion with multi-threading, but still having to play defense, where we insert blocking code when we need to block, when we want to make sure that we don't try to merge the left half and the right half together before they've been sorted in and of themselves. They need to finish their job of sorting first. Okay, so that means that when we create a thread, we need to have some way of that thread letting it know, letting its parent know when it's done. All right, so let's look at how that can be accomplished. So we're going to go and look at the documentation here for threads in Java. All right, so here's the thread class. I think I popped this up a couple classes ago or something at some point. So I won't, just as a reminder, since we didn't write threads for the last couple of classes, remember, built into Java is a class called thread, which implements this interface called runnable. And all that interface says is you have to have a method called run, public void run. That's what this guy is right here. So here's an example where they're inventing a class called prime thread, which extends the built-in thread class from Java. And they're going to write their own run method here. Okay. But the thread class itself comes with a magic function called start. And that magic function, that's the guy who knows how to deal with the operating system and ultimately get it to spawn off another thread, things that we would not have control with directly using the Java operating system. So we would call this thread class a kind of a very special class, since there's operating system level stuff built into it. and we don't get to know how the Java people wrote thread. We just know that it exists. We can extend it, we can inherit from it, and it already knows through its start method how to create a thread at the operating system level. So the only thing we need to do is make sure that we don't rewrite the start method. We don't overwrite the start method. In this case, we're overwriting the run method because thread's default run method doesn't do anything. So if we want our thread to actually accomplish stuff, we need to have its run method do some stuff. So we write our own version of that, which overrides the version we inherited from the generic thread class. That's what we want to do. What we want to make sure we don't do is we don't override the start method. We don't write our own version of the start method because we don't have the magic to tell the operating system how to create an actual true to life thread. All right. Whenever you're making threads, really all you're going to do is rewrite the run method. And notice up here that the constructor for your thread can take in some additional information. I think we may have shown that when we first introduced threads. I maybe had my threads taking names or something like that, so that each thread could announce who was printing whatever to the screen. But just imagine, if I'm going to say out loud for what will be helpful for your homework, imagine writing a thread that took in a pointer to an integer array, as well as a begin and an end value. So that thread knows the three pieces of information regarding the portions of the array it's working on. Okay? That's how you would want to write your threads. All right. So now as we scroll down here, we want to look at just a couple of the methods here that allow us to have threads talk to each other. All right. So one of them is called join. Well, so here's a couple of things. A thread can get its identifier. So every single time a new thread is created, the operating system assigns a ID to that thread, similar to, we looked at process IDs when we first were talking about processes versus threads. They were called PIDs. Every thread is automatically assigned a unique identifier. If we're interested in that identifier, for instance, if we want to keep track of the identifier of a specific thread, we can ask a thread to give us its ID. I don't think that'll be helpful for you on this assignment, but just kind of giving you that idea there. Threads can also have different priorities. That's not going to be important for this assignment, but know that you can create a thread with a higher or lower priority, which would then lead to the operating system either, forcing it closer to the front of the line for getting CPU time, or not necessarily forcing it to the front of the line if it's a low priority thread. Right? So if you imagine you're running computer, there are certain things in your computer that you want to be really snappy. Well, you want those to be high priority things. So whatever applications you're currently running, currently directly using on your computer, you'd like those to be as high of priority as they can be. Where certain things that are running in the background, like dealing with notifications or system backups or whatever, you kind of want those to, when there's extra time, when the CPU is not busy, go ahead and give them some CPU time, but don't let them change the end user's experience and have the computer slow down just so you can have some backup running, as long as it ultimately gets done. Okay, so that's what the priority thing is. Also not important for us, but this is just information that threads get. What we're looking at here is the documentation for the thread class and kind of seeing what are the features. What can a thread in Java tell us about itself? All right. We do have a thing called thread groups as well, where you can create collections of threads. This is good for applications that have a lot of threads that you're going to end up reusing. What you do is you actually pre-create your collection of threads so that during the runtime of your application, you're not wasting extra physical time spawning off new threads. You kind of have a pile of threads just waiting to start, already sitting there. Also, you won't need this for your assignment, but it's a thing. We do have this other thing, whether or not a thread is something called a daemon, which is like these would be headless servers. So sometimes you'll write a computer application that is just running in the background on your computer. These would be considered daemons. They don't really have a user interface, but they're performing something, and you can talk to them on the back end. A lot of times you would talk to them through network sockets and things like that. At some point, we might look at some network programming, but I want to get us into the Unity stuff as quickly as possible. So, we'll have plenty of opportunities during the next several years to look at some network programming. But if you're interested in that, you wouldn't want to look at the socket class in Java. And then another one's called server socket. Those two things would allow you to create things like chat servers or your own versions of um, uh, like BitTorrent, that kind of thing. Those are actually fairly easy applications to write. Okay, now we get to something that might be helpful for us, right? Realistically, this first one, this join one, is probably the most important. Now, notice there's 3 versions of join here. All right, they all have the same name, but they take a different number and or type of parameters. All right, this is an example. I think I mentioned it last semester, but I'll get it on a slide. We have something called polymorphism. This is when there are more than one version there is more than one version of a method with the same name, but a different number and or type of parameter. So in this case, we have a version of join that takes no parameters. We have a version of join that takes a single long. We have a version of join that takes a single long and then an int. Okay. These 3 things basically do the same thing with a couple of added features, but notice they're all void. They don't return anything. They're also non-static, which means they're instance methods. So we call them using an instance of the thread class. All right. And what the join method does is it waits for a thread to die. Okay. It waits for this thread to die, And we'll see this by an example here in a few minutes. This might be a situation where the thread that originally creates 2 worker bees, one for the left half and one for the right half, that parent thread might say, okay, I need to sit here and wait for my 2 children to finish their jobs before I can go and do the next step. So that parent thread would join the 2 child threads that it created so that it doesn't continue forward. And we'll look at this through some examples here. Let's see, anything else? Here's another one called sleep that probably won't necessarily be helpful in this assignment, but you can tell a thread to effectively pause. You can say go to sleep for some number of milliseconds. So if you want it to go to sleep for 3 seconds, you would put 3,000 in there, and it would go to sleep for 3 seconds. That's if you want to create little pauses. And here I can actually just show you that. Let's get some code going and then we'll jump back into this. All right. So I'm going to go ahead and I'm going to create a new file. And I'm going to call this guy merge sort worker b.java. Okay, remember I like to call my threads worker bees. So we're going to create another file called merge sort worker b. And we're going to go ahead and say class merge sort worker b, and this guy is going to extend the thread class. All right, and just so we don't forget, we're going to write our public void run. So we need to write the logic in here. That happens when this thread starts. All right. Now we probably also have a constructor for this guy. So we'll have public. Remember, constructors have the same name as the class name. That's true in Java. That's true in C++. It's true in C#, which is what we'll be using when we get into Unity. Constructors do not have return types because they always return a pointer to this object. Constructors are always called using the new keyword, which is our real estate agent that goes and gets us memory. All right. So I'll give you a little push forward with this. So I'm going to go ahead and say this guy will take in an int array AR. It'll take an int begin and an int end. When we construct a merge sort worker B, he's going to need those three pieces of information. I'm not going to need them for the example I'm about to show you, but I'll go ahead and put them in there because if your threads are going to be doing a portion of the merge sort, you're going to need some information, and we'll go ahead and put those in. We'll have a couple of private variables here. So private int array AR, private int begin, private int end. And then inside here, we'll say this dot AR is equal to AR. This dot begin is equal to begin. This dot end is equal to end. All right. But now what we're going to do here in run, just so you can kind of see how some of these things work, is I'm going to just put a infinite loop in here while true. All right. And what I'll do is, well, we'll just do this for a single thread first. So we'll say system.out.println. Hello, I am a thread going to sleep. All right. So we're going to say, hello, I'm a thread, and then we're going to go to sleep. We had just looked at the documentation here, and we see that there is a function called sleep and this causes the current executing thread to sleep. Now notice here, though, that this method is a static method. That means it's owned by the thread class. Therefore, we call it with the name of the class in which it was defined, which is the thread class. So we're going to say thread.sleep. So I'm going to go ahead and go to sleep, thread.sleep, and I'm going to sleep for just 1 second. All right. So because this sleep function was static, because of that guy right here, we call it using the name of the class as opposed to an instance of the class. All right. So what I'm going to do is I'm just going to leave it like this for now. And so the behavior here, and actually let me make it 2 seconds just so we get a very defined pause. So when I start this thread and I tell them to go, when I tell them to start, it's going to go into this run method here. It's going to say, okay, forever, what I'm going to do is I'm going to print something to the screen, and then I'm going to go to sleep. All right. So let's go ahead and see this work. So I'm going to go back to my main. And for right now, just so I won't dump your starting point here. I'll go ahead and just comment out the stuff that's currently in main, because you're going to be converting our current merge sort into a multi-threaded version. I'm going to go ahead and give myself an instance of merge sort worker B. So actually, we'll just do that. I'll go ahead and still create my array. I'll fill it up with random numbers. But then I'm going to go ahead and create an instance of merge sort worker B. We'll call this guy WB for worker B. This is going to be a new merge sort worker B. And this guy expects me to pass it an array, a begin, and an end. even though I'm not technically using those things yet. This would be what you're going to pass your threads, something along those lines. You'd pass it the array and the portion of the array that thread is in charge of. So there's my worker bee, and I'll tell my worker bee to go ahead and start. Okay, I created a single worker bee. I tell them to start. What does start do? Start says, okay, I'm going to go to run. While true is true, which is going to be forever, print something, go to sleep for 2 seconds, spin back up, print it again. So rather than having things just turboing on the screen one line after another, we should see a defined pause between these things. Go ahead and run this. So we have stuff in Java. It also exists in C# called exceptions. So we have this unreported exception called an interrupt exception. So the sleep function here, if I go back to the documentation and I go to sleep and I click on that, notice this guy does something called throws interrupted exception. Couple of ways you can deal with this. I'm going to do the cop-out version right now, just for time, but I'm not going to handle that exception anyways. So one thing we can do is we can go ahead and just say, I want to try to do all this stuff and then catch any exception that might happen. And the stuff I'm going to try to do is this while loop. So actually, I didn't do the cop-out. This would be probably the correct way of doing it. All right, so we use something called a try catch. And I'm just going to choose not to do anything when I catch. We can throw a system. Actually, there's a e.print stack trace, I think is what it's called. This will just print the error message to the screen, or you can say system.out.println. Something went wrong with our thread.sleep. I don't expect to see this error, but because it possibly throws an exception, we have to then deal with it. So we are going to try to do all this stuff and catch a problem if it happens. I'm going to try to forever print something, go to sleep for 2 seconds. So there's printing once, 1, 2, 1, 2, 1, 1,000, 2, 1,000. Okay, so we're seeing that that cadence, right? All right, so let me stop this. So now we see that we can have a thread take a break. We're probably not going to have our threads take a break in this particular program, but we do want to have some communication between our threads. So I mentioned we had this join method, this guy right here, which waits for a certain thread to die. And join is an instance method, so I need an instance of the thread class in order to call this guy. And it just so happens here in main, I have an instance of the thread class called WB. So I can go ahead and say, I can tell that thread to start, and then I can say wb.join. And then I'll do system.out println, I'm back. Okay. And what I'm going to do here is I'm going to say int I is equal to 0, while I is less than 3, do this, and I'll have it go to sleep for roughly 1/3 of a second. So it'll go a little quicker. It'll do this 3 times. I plus plus. So now my thread is going to go and do something 3 times and then ultimately end when it hits the end of the run method. All right, this is no longer an infinite loop. Now it just does it 3 times. And when I first created that thread, I told the thread to get going, but then I also, my main thread, this guy, the guy that's part of my main, the thread that came with my running program, I'm telling him to go ahead and join the thread that we just started, which will cause him to, as you see, wait. This waits for this thread to die, waits for that thread to finish its job. All right, so we'll go ahead and run this. Oh, another exception. All right, this is where I'm going to, this is the cheating version of this. I'm just going to tell main to throw any exception. That means it'll be whoever ran main's problem, which is the Java virtual machine. So I can either wrap all of this in a try catch like we just did, or if I don't intend to do anything with the exceptions anyways, I'm just going to tell main to do all this stuff. And if there's ever a problem, just throw it. So now it's going to be fine with me running that code. All right. So notice here that my thread completed before I ever got to this line. So what I effectively did here is we created a block, blocking code section that won't continue until the thread is done. All right, makes sense what that guy's doing. So I think that's all you're going to need to accomplish your assignment. So your assignment is effectively the same merge sort assignment we had before, but instead of recursion, you're going to use threads to implement it. All right, does that make sense what I'm asking you to do? So you will have 0 recursive calls. Instead, when you need to deal with the left half and the right half, you will create 2 threads and tell each one to go and start working on their portions of the array. But then you need to tell the guy who created those 2 threads to wait until they're done before he can do his merge step. All right, questions, comments, concerns, bribes? All right, so I'll put that assignment up. Remember, get Unity installed over the weekend if you want to have it ready to go for class on Monday. And I'll put this assignment up with this as starting code. And remember, I've kept all my merge sort solution in here. I just have the last part of this commented out since you're not going to be using it anymore. Okay, have a good weekend. I will see everybody back in person on Monday. All right.